Hey everyone, this is Mr. Ference. I hope you're doing well. We are going to keep going with our lecture on fluid mechanics. This next section is on fluid dynamics, so that's fluids that are in motion. A quick sort of vocabulary clarification. When a fluid is fairly slow, it's smooth, it's regular, we call this laminar flow, and we see this up at the top of the diagram. Once it gets moving above a certain speed, and what that exact speed is depends on the situation. But we see what's called turbulence. We start seeing these sort of whirlpools called eddies, and it gets very challenging to calculate. It gets very complex. In this course, we are just going to be looking at laminar flow. It's beyond our capabilities right now to calculate turbulent flow. So just keep that in mind. We can measure the flow rate of a fluid. This is defined as the volume of this fluid that is going past a particular point in a given time. So this is volume per time. This is measured in cubic meters per second, or sometimes gallons per second, cubic yards per second. But the thing to keep in mind is when it's flowing through a pipe, we assume that this pipe does not have leaks, that it's keeping all of the fluid in the pipe. And so this flow rate, Q, again measured in volume per time, this flow rate is just going to stay constant. Keep that in mind, because we may see often these situations where the pipe itself, the dimensions of the pipe are changing, where it could be getting bigger, it could be getting smaller, and that will change how the fluid moves through that pipe. So a couple of things I want to point out here, a couple quantities that we need to be aware of. We have here this pipe where it's moving from a larger section of the pipe to a smaller section. Each section has what we call a cross-sectional area, A1 and A2. We assume that that's a circle, all right? We wouldn't make a square pipe that's not stable. So we're going to assume that these cross-sectional areas are circular. It's moving through these pipes at a certain velocity, V1 and V2. These are probably going to be different. If the size of the pipe is changing, they're almost certainly going to be different. And in this given time, whether a half a second or a second, whatever that time that we're measuring this for, the fluid itself will travel a certain distance. Here we're calling that delta L for length. So it's traveling delta L1. In that same amount of time, it's traveling delta L2. Now, we talked about how this flow rate is going to be constant. What that means is that this expression here, V, the volume divided by time, is going to be constant. But think about this in terms of geometry. If we look at this section of pipe as a cylinder, remember that the volume of a cylinder is it's the area of its base times its height or its length. And so we can actually rewrite this as A, the area, times delta L, that distance, divided by time. But keep in mind also that distance divided by time, we can just rewrite as velocity. So this will actually simplify to area times velocity. This is little v velocity. This is big V for volume. They are not the same thing. Just keep that in mind. So in this pipe, if this flow rate is constant, what that means is that the product of the area and the velocity have to be constant. So if we compare the product of A and V here at point 1, it's going to be the same as the product of A and V at point 2. And that gives us a very useful equation. This is called the continuity equation, or the equation of continuity. It's pretty straightforward. There are no squares. There are no fractions. There are no square roots. We're just looking at the product of the area and the velocity at two different points. The main thing to take away from this equation is that there is an inverse relationship between area and velocity. As we pass from area 1 to area 2, if here, I'll draw my little pipe here. Okay, so here's that area, right? So this is area 1 and area 2. If area 2 gets a lot smaller, in order to keep this equation true, the velocity that it goes through will increase. Keep that in mind. That's something, if you come down to downtown Richmond, if you go down to the river in the middle of the city and go to the rapids like Belle Isle or something, you will see that as the water is forced through these narrow channels between the rocks, the room that it has to maneuver is pretty small. So the velocity is going to be very, very high. Once it gets past these rapids and it goes out into this big tidal basin that's nice and wide, a much larger area, the speed of the current is going to drop significantly. So keep that in mind. That's going to wrap it up for this video. Keep watching for the second part where we talk about Bernoulli's equation. Until then, take care of yourself.